All right, welcome to the third part of our basic or fundamentals of statistics. And in this part, we'll be looking at measure of dispersion. So in statistics, measure of dispersion describes how spread out a set of data is around the center. By the center, we mean the mean or average. If you look at this bell curve, you are going to see in the middle here, we have the mean, right? And you see the dispersion around this mean for this curve, you see that that dispersion is small. A larger curve means a wider or larger dispersion. We could also just basically state that measure of dispersion is a measure of spread of data about the mean. So we have the range, the variance, and the standard deviation. Those are the three measures of dispersion that we'll be looking at. And as usual, we have Excel sheets or worksheet for us to demonstrate these measures of dispersion and how we can work on them. So why is measure or understanding measure of dispersion important? When we understand how dispersed data is around the mean or the central point, it helps us to understand. We talked about outliers yesterday. Let me just give a practical example. Let's say you have an expected, an expected deviation. In research, basically, I've experienced that when you do research and say you are collecting a weight, say weight of albino mice, all right? When you're collecting the weight of albino mice and the weight, the albino mice basically are supposed to have the same age or be in a particular age range. It's expected that their weight will vary, however, not vary so much that the deviation will be very wide. So we want to use, say, a weight of, let's say, 2 kilogram plus or minus 0.5. So we know that the dispersion is so small. So there are various practical applications. Okay. For instance, now, when you take a height of, say, height of children aged 5, and from a particular sample, right? So it's expected that you don't measure somebody at 6 foot tall at 5, right? Because when you do that, and others are just about 2 feet to 1 feet, you basically will have a wider dispersion. And we are going to see how that works here with our data. Let's go to our Excel spreadsheet. We said we have three important dispersions or measure of dispersions that we are looking at today. And the first is range. Okay, so what does the range do? Okay, so in the range, we want to see the difference between the largest and the smallest value in a distribution. That is what we want to see. Okay, so we want to see, using these two populations, we want to calculate the mean now. Remember, we talked about mean in central tendencies, right? So now let us calculate the mean. And we say in Excel, we can basically calculate the mean by using average, right? So we'll say equals average. We just highlight the values, close our parentheses, and we basically get this as our mean. So let me just add one column here so that I easily just call this mean for us to remember. So although we have different these values are different, let us see if we calculate the mean here, if we have the same value, because I want to ensure that we have the same mean so that we can basically discuss further. So yes, we have the same mean. We have a mean of 10. So if we describe range as the difference between the largest and the smallest value in a distribution, so range will definitely be, range will now, we will say range will be L minus S, right? The largest value minus the smallest value. So that is what we'll say range is, okay? So definitely we will be able to say, so range is equal, right? Largest value subtracted from the smallest value. So this is what our range will be, okay? So if this is what range is, to calculate the range for this population, for this first population now, the largest value here, okay, the largest value here will be, okay, so we have the largest value here as what, 11. So in this case, we have 11, which is the largest value, right? Minus 9, which is the smallest value, okay? So that is what we get in this case. And if we further, 11 minus 9 will give us what? That is 2, right? So let's say 2. Let's just have this here, okay? Now, we come to this population. We have a mean of, right, of 10 still, isn't it? So now, if we come this way for this population and say range here is the largest number minus the smallest number. So the largest number here in this case is 17, and the smallest number here is 3, isn't it? So that means it should give us a range of 14. Okay, so now we have two populations having similar means, but we are having different values for our range. What this shows us is that the dispersion between the individual values in this distribution. If we look at the first population, we will see that the difference between each value isn't much. And so when we go back to our measures of dispersion, we can see that for the first population, we can see that the dispersion is small, okay? It's small because it's centered around the mean, okay? Now, look at this. Let's go back there. The mean is 10. The difference between 10 and 10, no difference. Between 10 and the mean, no difference. 11 and mean is just 1. 10 and mean, no difference. So we basically have a difference of 9 and 10 just beside the mean. So this is quite a small dispersion. But when we come here, we are going to see that we still have a mean of 10, but we have 17 here, right? So there is a wide dispersion with the difference between 17 and 10. We have 3, which is the smallest number. There is a wide difference between 3 and 10. So we can see that the dispersion in this second population is definitely larger. Okay? So this is just the first measure of dispersion, range. So the second we are looking at, or we are going to be looking at, is variance. Okay? So now for variance, what is variance? Variance is the measure of how far a set of numbers are far apart or spread out from their mean. How far? Just like basically what I described now, what I described when we're talking about range and using the bell curve and so on. So now I want to clarify that we have two kinds of variance. In statistics, we have the population variance and we have the sample variance. Okay, the difference is that if it were in the sample variance, the formula would differ a little bit. It would just be n minus 1. And I'm going to tell us what this means, what all this stuff we have here mean. So to calculate the variance, excuse me. To calculate the variance, what we need to do is basically to get our mean, okay? Now, this is summation, right? This X here mean value in a distribution, for instance, in this case, 9, right? Minus the mean. This sign symbol here means the mean. So we will calculate the mean here, which the mean here should be 10, right? Okay. And the mean here should be equals average. The mean here should be 10 as well. Okay. So we have the means already calculated. So now what we want to do is to subtract each number, right? Each occurrence from the mean. So we will say in this case, we'll say this, equals equality sign, this minus our mean. Okay. Let me take this out of table, convert to ranges, and convert to ranges as well. So, okay. So we want to say the equality sign, our value here minus our mean. So to make sure that we can, as usual, just take it down without any issue, we just have to lock that cell, okay? We'll say F4 to put our dollar signs this way and lock that cell. Okay, so now what we need to do now is just to fill this up. All right, so what we had done here was to calculate the mean, right? And then subtract our numbers, right? From our mean. And if you look at this, 9 minus 10 will give us -1. 10 minus 10 is 0. And that is how it went down. So we want to be able to calculate say the square of our value here of X minus mu. X here, like I said, is the individual number in our distribution, the value in our distribution. X minus mu here gives us this value here. That is, mu is our mean. So we want to square it so that we just have this. When we square it, then we sum it. That is what we have to do here. So what we need to do now is to say this, okay? So 1 square is 1, right? And we know that 0 square is 0. We know that 1 square is 1. So when we take this across, so we basically get our answer for that calculation. So we get the 1, the zeros, the 1. So our sum of these, let's say, equals to sum. Our sum of these will be 2. So now, if we were to we want to go ahead now and calculate our variance for this population. Our variance for this population will be 2, right? Let's say variance. We already calculated to say our variance will be equals to 2 divided by n. N is the number of population. So we have 1, 2, 3, 4, 5. That is 2 divided by 5. So when we do this, we are going to get 2 divided by 5 will be 0.4. So then let's calculate the variance for the second population. We had calculated the mean already. So all we need to do is to subtract our value in our distribution, individual values in our distribution from our mean. So to do so, in this second population, we'll say equality sign, say 3, right? Minus 10. So we have to lock where we have our mean, right? Okay, so there's the value we have, then we go down. So if you look at it, we have 3 minus 10 for the first one, and we have negative of 7. We have 7 minus 10, we have a negative of 3. 10 minus 10 is 0. 13 minus 10 is 3. 17 minus 10, a positive of 7. So let us calculate the square of these, and we will just calculate the square of 7. We'll just do that, and we will have the square of 7 as 49. So we want to also calculate the square of 3. When we drag this down, it calculates the square of 3 for us, which is 9. So we take it all the way down. Now, I want to clarify that you don't calculate it in such a way that you maintain the negative 7. So you just take it as 7 as it is, okay? All right. So let's calculate the sum of, that is the summation of this value. Okay, so here we have the summation of the value. So to get our variance for the second population, we then have to say our summation, right? So which in this case was 116 divided by the number of population, that is 1, 2, 3, 4, 5. So divide by 5. So now if we do this, we can just do this by the side and see what we have. So we'll say equals 116 divided by 5. We have 23.2. So our variance here will be 23.2. So we can see that the same number of population, the same mean, but we are having different variance. Just as we saw, as we had a different range for the same number of population and the same mean, okay? So the last but not the least will be the standard deviation. Like I made mention when we're discussing a variance, I said we have the variance for a population and a sample variance. So we have two kinds of standard deviation. We have the population standard deviation and the sample standard deviation. And the difference here is that the population standard deviation is signified by sigma, while the sample standard deviation is signified by S. And the second difference is that in the sample standard deviation, we subtract 1 from our sample size, N, okay? Whereas in the population standard deviation, we don't do that. So to do this, we definitely have to calculate our mean, right? And we say to calculate our mean here in Excel, we will have to do equal average. Then we'll take this as a range. Okay, so we have our average as 10, okay? So let me use this so that we know that that is our average. So we need to subtract these individual values in our distribution from our mean. So we will say equal this value minus our mean, okay? So we have to lock our mean so that we can easily just autofill, okay? So we autofill it, drag to autofill, then we have the value. So we have to calculate the square of this value. So what we have to do now is say equals. I want to square this by multiplying it by itself, okay? All right. So we have 49, the square of 7 squared is 49, and we take it down, we have that. So we have to sum it. That is why we have the summation sign here. We have to sum that. So we'll say equals sum. We want to sum the values in this range. So we have 116 here. So what is left is for us to do what? To divide this, right, by the number n, then find the number of population n here, the total number of observations rather, then we find the square root, okay? So if we do that, we can say SD in this case, that is standard deviation in this case, we have 116, right? Divide by total number of observation will be 5. So when we do this, we get the value, then find the square root of that value, okay? So let's say this now, we have 23.2. 23.2, we get that value. So we have to find the square root of 23.2, okay? So the square root of 23.2, here we have, we'll say 4.8, okay? This is the population standard deviation, and this is sample standard deviation. Let me explain so that we know the difference. The difference here is that, assuming, let's read this question. The researcher collects data on a number of hours spent studying by a group of students for a week. Let's say this is the entire group, right? The group of students he studied, this is the entire population, right? So we didn't have to pull a sample out of a student. So this serves as the population, right? But in this case, let us assume that this group of students were just a sample out of the entire students. So that is the difference here. And we are going to calculate the standard deviation just so that we see the difference, okay? So now let us, we have basically, these values are the same. So we are using the same values. So let us just go ahead now and say, we want to basically get the square of these values, okay? Okay, so let's autofill this. So we autofill this, we get our sum. I think we should get the same sum definitely, which is 116. Okay, so we get 116. So we want to now look at the total number of observations. Our total number of observation is 5, right? 1, 2, 3, 4, 5. But for the sample standard deviation, we have to subtract 1. So definitely, our total number of observation becomes 4, right? So our standard deviation will be equals to the summation of this year, which is 116, divide by, say, 5 minus 1, because our total number of observation here is 5. So we have 5 minus 1. So this takes us to 116 divided by 4, because we have taken out 1. So when we do this, we have 29. Okay, so we need to find the square root of 29, okay? So the square root of 29 now is going to give us our sample standard deviation, okay? So it gives us 5, okay? So our standard deviation in this case is equals to 5. All right, so what if we wanted to basically check the difference between these two populations, right? In which case we want to actually check the standard deviation in these two populations. So let me put this here so that we'll basically look at this, okay? So we have this, and this equals this minus the mean here, okay? And let's log this and autofill quickly. All right, we autofill and we get our values. Let's get the square of these values, in which case we will, so we've gotten the square, so we have to. So if we want to calculate the, say, the population standard deviation for these values, this set of values here that have a similar mean with this set of values, let's see which will have a higher standard deviation, right? So to check this now, we have our sum here. So we could easily just calculate this way. So we have 2. In this case now it will be 2 divided by 5, which is going to give us 0.4. Okay, it's going to give us 0.4. So now therefore we have to find the square root of 0.4 to have a complete picture of our standard deviation. Okay, So then in this case now, our standard deviation now will be equals 0.6. So you see now the same mean, the same total number of observations, similar mean, similar number of observation, but we have a standard deviation in this case, in this population, lower than this other population. The difference between the values in the data distribution we have here from our mean is not so much. And that is why when we're talking about standard deviation, we say standard deviation is the deviation of the values from the mean, okay? Is the deviation of the values from the mean. And you see here that this deviation, the deviation here, let's say is say plus or minus 0.6. And if you look at it, it's actually true. So when the standard deviation is low, it means that our values are close to their mean. The values are close to their mean. In this case, this standard deviation is higher than this one. So therefore, some values here are far away from their mean. That's what it means.